On my newly set up Raspberry Pi, I have OpenSSH installed, so that way I can SSH into my Raspberry Pi, which is running Raspbian, right? And let me just type an SSH right into the Raspberry Pi. You see that I'm in, and we'll go ahead and update Raspberry Pi, upgrade all the packages. We'll just skip this for now because it's trying to download LibreOffice, which we really don't want. But before that, let's talk about the space requirements. One thing that you have to understand is that OpenCV can take up quite a lot of space to compile, probably around 4 gigs. So you have to make sure that you're not using a 8 gig card, right? And then you might have to use a 16 gig card so that you have enough space to compile OpenCV comfortably. Now, however, if you're stuck with an 8 gig card, here is something that could work. You could remove some packages which are installed on your Raspberry Pi. For example, we see that LibreOffice is installed here, which is something we definitely don't need, right? Now, let's see which packages are actually taking a lot of space. And for that, we could install a package called Debian Goodies, which contains the dpigs utility, which will actually show you the kind of packages that are taking a lot of space on your system. It makes it really easy to do that. So let me go ahead and install Debian Goodies, as you can see. Now I'll run the dpigs command from Debian Goodies, which will show us the top most space consuming packages. I'll add the -h, capital H option to show the same in a human readable format. So you can see that Wolfram engine and LibreOffice and all those packages are taking quite a bit of space. So of course, you can't remove packages like the kernel, but you're free to remove other packages like Scratch and Wolfram engine if you're not gonna use it. So let me remove some of these packages here. Now let's remove some packages that aren't needed. These aren't needed anymore because we uninstalled a bunch of packages, and these essentially were just dependencies of those packages. We have a bunch of dependencies to install. This is going to take a while. Let's come back after these are installed. Our dependencies are now finished installing. Because I've SSH'd into the Raspberry Pi, it's actually a good practice to have tmux running. If you don't know what tmux is, I'll leave some notes in the video description. You can read about it here. But more importantly, if you want to do some kind of a long running process, and then you want to shut down, or you want to put the computer to sleep, from which you essentially have logged into the Raspberry Pi, you could do that. And this makes sure that the session is not killed or anything, and then you can always log into the Raspberry Pi later on. So let me go ahead and do that. I'll start tmux now. I'll clear the screen. Just to demonstrate what this is capable of doing, let me install Vim and let's say htop. And while this is installing, this lets me disconnect the Raspberry Pi completely. And I'll log out of the Raspberry Pi. I'm back to my iMac. Let me log into Raspberry Pi again. I've dropped into the Raspberry Pi, but you can see that our process is actually still running. Here is our command, and I can attach myself to the session by doing tmux attach. So here I am back in the session. This is very useful because we're going to compile OpenCV, which can take hours and hours. Okay, we are done with Vim. So the other problem with compiling a package as huge as OpenCV is that you can run out of memory very quickly, right? And if you look at it right now, we have 100 MB of swap, and then we have about like a GB of memory left. This is far from enough when you are considering compilation of a package like OpenCV. So now we're gonna increase swap to about a GB at least, so that we can successfully compile OpenCV. For that, I'll have to edit the swap file here. I'm going to change this to 1024. Save this file, and I'm going to now restart the swap service. Which will then make swap 1 GB, which should be enough, right? Now you have to be a little bit careful here because the Raspberry Pi is running off of a SD card. Now SD cards ultimately are flash devices, so you have to be careful, what you do with them. They cannot take a lot of writes like traditional hard drives. And now, for example, flash memory typically has a 10,000 times cycle after which it starts wearing out, right? And then some embedded systems actually use something called wear leveling, where the file system is aware that it's running on flash, and then it tries to use or rather spread the writes, right? Now nothing of that sort is actually happening here because it's just considering the SD card we operate on just like any other hard drive, right? Now that's a problem because it can wear your SD card very quickly, and because you're using swap space on the SD card, the operating system will try to swap out programs very often, and it can wear out the SD card. Now, as a general good practice, it's actually a very good idea to have some file systems which are known to do temporary writes. Now let me log on to another system I have, which is like a homemade NAS server, right? Just to show you, what I generally do. This is a very tiny system. It only has a total of 128 MB of actual RAM. But then again, what I'm doing is I'm creating small 16 MB RAM disks to have directories like verilog and then tmp, so that this system is also running off of a flash thumb disk, right? And this ensures that when many changes are getting written, they are written to the RAM disk and not to the flash disk. And this is a really old flash disk, maybe more than 2 years old, and I've had no problem with the system. Now let's go back to our Raspberry Pi. Log out from here, go back to the Raspberry Pi. Now let's install pip, because we want to install certain packages, Python packages, right? We're gonna execute the script we just downloaded using Python 3. Now using pip, we'll install virtualenv and virtualenv wrapper, which we will use later on. We'll now set up some variables in our file. This will help us out. Now these will help us with the virtual environment setup. As a comment I added just in case I forget tomorrow, so that I don't have to log out, so that I get the variables. I'm just gonna source my profile. So let's set up, it's running Python 2 by default. Let's set this as well so that it can run. I'm fairly sure it's user bin Python 3. So let me run the source command again. Perfect, we're good. Now let's set up a virtual environment called CV, which will be used to host our OpenCV Python module. So we are creating a virtual environment and we are specifying the Python interpreter as the Python 3 interpreter here. Or it might take Python 2, which is probably the default. Take a look at the command prompt. So this says CV, which means that this particular virtual environment is active right now. Now, whatever you install as far as Python is concerned will get installed into this virtual environment. It won't affect the full system's environment, Python environment. So we'll be needing NumPy. Let's install that. Great. Now let's set up a working directory where we can install OpenCV. This will be it. We're gonna download the source code for OpenCV now. Let me untar this now. Now let me get OpenCV contrib, which is a very important set of features of OpenCV we will need. Let's untar this. We should now have two directories, one for OpenCV and the other one for OpenCV contrib. Perfect. Now let's get into the OpenCV directory and make ourselves a build directory there. We get into that directory and start building OpenCV with this huge, humongous command. We are enabling Neon and VFPv3 instruction sets. This makes OpenCV faster on the ARM processor, which is there on your Raspberry Pi. So this should configure OpenCV. Let's try this. Since we are in the CV environment, it's taken the right Python interpreter, which is great. We want this to be taken. And now we could check, for example, how many CPU cores our machine is having. You can see that it has 4 cores. I'm running htop here. You could also do cat proc CPU info to see how many processors are there. As you can see, we have a total of 0. It starts from 0. You have CPU 0s, processor 1, 2 and 3, which is total of 4 processors. Now with this we should actually be able to speed up make quite a bit, because we don't have to, if you just run make, what will happen is there will only be one CPU core that will be used, and making the whole process really slow. But if you do -J4, because we have 4 CPU cores, make will actually in parallel compile as many as 4 different files, right? So let's do exactly that. Now it's begun building OpenCV, but the whole point is that it's going to take a hell of a lot of time. So I'm going to go get some shut-eye time, and then because I have tmux running, I can disconnect from the system. I can always come back in the morning and then take a look at how our OpenCV compilation has done. And just for fun, because we are running make-j4, we could take a look at how well all our cores are. And as you can see, all 4 CPU cores are being used fully, because we told make to essentially run the compilation on actually 4 different cores. So you can see that all 4 cores are firing right now, and let's hope that this doesn't fry up the little Raspberry Pi board we have, but we should be okay. Swap hasn't started getting used, but I believe it will get used, especially during the linking phase, where several libraries are linked together, and the linker will take up a lot of RAM. Now I'm gonna go get some shut eye, and I'll see how this thing goes in the morning. I got some good sleep. Now I'm gonna SSH into the Raspberry Pi to see how things went with our OpenCV compilation. Let me go there. Okay, and I'll get into the tmux session to see how things went. 100% done, and we're done successfully. I don't see any errors except for a few warnings, but that's totally all right. We'll now install OpenCV. That's a very simple command to take care of that. Once we are in the build directory, you just do su make install, and that should start the installation process. It'll take a while. Now that is done, I'll run ld config to ensure that the latest libraries are available to newly running programs. And now we should have the SO file, the shared object, available in the locally installed Python environment. User local lib Python 3 in our case, local lib Python 3, and site packages should be here. This file, we don't want it to be named like this. We want it to be named cv2.so, and that's exactly what we'll do. We'll rename this to cv2.so. all right, and then let's check that rename. That went well, and I'll also ensure that this is made available to our virtual environment, which is in CV. So it's same thing here, Python site packages. All right, I need that to be available here. So first is I need to give the source rather than the destination, which I will do. I'll copy the source from here, and I need this here under the same name. Okay, now let me quickly do an ls and check whether we have the link. Perfect. Now that points to our Python cv2.so. I'll also check whether we are able to successfully load and check the version. I'll just do import cv2. Let me clear the screen, and that seems to be a success. And I'll also do a version check very quickly. Yeah, 3.4.1, and so we have OpenCV2 installed. Now I don't want to stop there. I just want to run a small script, a small Python program, to ensure that everything is okay with OpenCV. I don't see why not, but this is a very simple face detection program. It captures frames from the camera, which I have attached to my Raspberry Pi, and then it uses HAR cascades to detect a full frontal human face, and then it draws a rectangle around the face through this line. It's a very small program, as you can see, not many lines long. It's exactly 42 lines long. Let me exit Vim and try and run this program. Let's see what happens. It's complaining that it's unable to open the video device, which means that I don't have permission. This particular user doesn't have permission. So that's a very simple thing to fix. Let me do this. Basically, I'll specify the group to add to the user, and we should be okay here. Let me log out and log in again so that this takes effect. Go back into the project directory and run face detect.py. Okay, I'm not in the environment. Work on CV. Let me rerun that command once I'm in the virtual environment. Okay, it's opened up the camera. You can see my face. The Raspberry Pi is right in front of it, and it's detected. Yeah, that looks scary because this is a infrared camera. It can see infrared, and it's got infrared light as well. Okay, there we have everything running. So once we cross this step, you'll be able to do a lot of interesting things with OpenCV on your Raspberry Pi. It's a little bit slow, definitely slow, but the fact that it can take a camera and then you can do a lot of things with it is very, very interesting. I'll see you in future videos where we do a lot of more interesting things with the Raspberry Pi and the camera with OpenCV. Bye now.